Can you hear me?
Yes. Yeah.
Good. Yeah. Hello, everyone. This is Mustafa. As Ime said, I will be discussing something linked to automated algorithm design, which is combining different ideas in algorithms, which are hyper-heuristics and algorithm selection, and try to come up with a system which could solve different problems under one scenario. So let's see what we have in here. So this is the outline I'm going to follow. Initially, I will briefly talk about algorithm design and the challenges we are facing. And next, the discussion will be on the selection hyper-heuristic, which is helping a bit to automation or the issues you have with the algorithm design. And algorithm selection will give us a new perspective, providing automation. And then I'm going to combine these two and come up with a system called cross-domain algorithm selection. And next, I will be presenting results on 9 different combinatorial optimization problems, then finalize my talk with short conclusion and briefly mentioning what I have been doing lately on this topic. So let's first look at the algorithm design, right? This is kind of everyone is doing, right? Almost everyone. And you don't even need to be in computer science. Maybe you're in the medical field, you're also probably looking for an algorithm like treating a patient, right? So in our case, of course, we are solving those computational search problems, and we could come up with different types of algorithm by combining different ideas, by changing different parameters, which will give you an algorithm design at the end. But this is tend to be problematic because the search space or the design space is huge. So that's why we are seeing a lot of algorithms, like there are problems that algorithm is developed. A few months later, anyone is coming and saying that I'm doing better than the previous one. But to do that, we need to go over 3 major elements. And one is we need to, of course, know how to develop an algorithm in the first place. And on one side, you need to know things like programming, data structures, and algorithms in general. And next, we need to know the problem we want to solve, right? So we need to have some level of expertise. In real life, this is mostly happening in a way that there will be someone who knows the problem. You kind of collaborate with that person to learn about the problem and devise a solution to solve it. But this is not enough to design an algorithm yet, at least a good one. You need to go through usually a substantial implementation period. This simply means that you're going to design an algorithm and you will take a look at it theoretically, probably check its performance mathematically, and you convert it into implementation really. And at that point, what happens is you're going to test it and you're going to find bugs and errors and you're going to fix them. And then you will be seeing some performance issues that needs to be still fixed, right? So this doesn't happen quickly. And also when you deal with algorithms, you will see that there are different versions of them because they are finding some issues which are happening in the previous version. So they are handling or eliminating those aspects. So for that reason, we are having those algorithms which are coming with the premature commitment. Because what happens is, like for instance, if you want to write a paper, right? You're going to pick a topic and you will design an algorithm. You will rely on your like an experience or background, and you try to combine them. Whenever you get an algorithm which is good enough, you will be happy, right? But of course, the problem is we are committing those decisions too much. So if we can automatize this process, we can likely to generate a better algorithms at the end without using too much human resources. So let's look at one take on this algorithm design aspect with selection hyper-heuristics. So the hyper-heuristics are essentially algorithms which have been used on various computational search problems, and they have been introduced to devise systems which are problem independent, which means that you're going to take an algorithm which is a hyper-heuristic and you will be able to apply it to a variety of problems without changing the algorithm part. And the goal was initially to devise good enough a solution. So it means that the quality may be not the best, but it is all right. Soon enough, so we want to get the solutions quickly, right? We don't want to wait. And cheap enough, which could be considered in the sense of the computational computation resources unit, and the human resources you need to invest for designing the algorithm. But then we realized that there has been those different hyper-heuristic studies showing that applied on different problems, showing that they are not just good enough, soon enough, or cheap enough, but they can actually generate state-of-the-art results. So that's why now we are seeing a lot of hyper-heuristic implementation, and they are not just in the academia. There are tools in the industry that have been using hyper-heuristic to solve all kinds of computational search problems. So then what kind of hyper-heuristics we have? So initial type of hyper-heuristic we have been discussing is on the one on the left-hand side, which is called selection hyper-heuristics. So it simply means that we have problems, different problems, and we have heuristic set. And heuristic set means that we have a set of algorithms, and those algorithms usually tend to be operators, right? They're making small changes on the solution, but they could also be complex algorithms. That's also possible. And on top of that, you're seeing we are having this domain barrier. And the selection hyper-heuristic is essentially trying to solve those problems underneath without knowing them by simply managing those heuristic sets. I will further explain this process later. And the second type we have, which came out after the selection hyper-heuristic, but the idea was kind of there already, is called generation hyper-heuristics. So for this one, the idea is automatically devising algorithms for a given problem or problem instance. And so for the generation hyper-heuristic, to give you some examples, and the initial ones were generally utilizing genetic programming called grammatical evolution, if you know them. And also the kind of the later version, they have been using parameter tuning. So the focus of this study will be on the selection hyper-heuristic. So I will continue with that one. But before moving to the selection hyper-heuristic, I would like to notify you something about the term, right? If you don't know hyper-heuristic, you might think that, okay, I'm recalling this name from somewhere, right? So that's why we have the meta-heuristic. This has been the one of the major algorithms when you don't have an optimal solution, and the solution is computationally challenging, and you come up with an algorithm which is generating somewhat good results, right? So these are great, that's good, but the thing is they are essentially those algorithms. We can call them as universal algorithm frameworks, because the problem with the meta-heuristic, when you pick one, you need to tailor it for the problem you're going to solve. To give you an example, you could find, for instance, table search, right? There are a lot of papers, but if you look at each one, you will see that they are designed differently. On the other hand, with the hyper-heuristics, we have, as I already mentioned, we have this problem domain, right? Domain barrier we have. So that domain barrier makes sure that we don't touch the problem. We don't know the problem. So basically, whatever problem you throw at, it will be able to solve it in a good or bad way. We will talk about that shortly. So from the beyond the problem independent perspective of the hyper-heuristics, one thing we are interested in is the generality. Because we have this kind of a system which can solve different problems at once, and we would like to make sure that it is also doing a well job, right? Because we just don't want to apply them, we also want them to work well. So that's why there are a number of steps we need to take into account when we are working hyper-heuristics. One is a good hyper-heuristic should be able to solve different problems, of course, because it's problem independent. Second one is a hyper-heuristic is expected to work well on instances, on variety of instances of a particular problem. And the second aspect, the hyper-heuristic part with the low-level heuristics, especially the selection hyper-heuristic. So when we have this different characteristic of the heuristics, we should be able to deal with them. So we shouldn't be working on just one type of heuristics, then the hyper-heuristic is working well. And the other thing, again, especially for the selection hyper-heuristic side, we could have different size of heuristics available in the heuristic set. Maybe in one case you have 3, in the other case you have 300. Your hyper-heuristic can handle that or not. And the last aspect to referring to generality will be on the experimental conditions. So your hyper-heuristic are expected to work well with different stopping criteria. So it means that maybe you have an hyper-heuristic which is really working well if you give long time, or it's working well if you limit the time in comparison to the other algorithms utilizing the same time. Of course, in the literature, it is kind of hard to find a hyper-heuristic which is doing all of them in terms of generality, but there are different studies focusing on different generality aspects. So this is the selection hyper-heuristic. I already showed you a visualization. This is purely on the selection hyper-heuristic. So now that you can more clearly see that at the bottom we have the problem domains. There are different problems. And we have the heuristic sets, they're attached to the problems, and we have the domain barrier, right? And on top, we have the hyper-heuristic part. In a selection hyper-heuristic, which is usually composed of two parts. One is called heuristic selection. It is responsible for picking the heuristic while solving a problem instance, right? Because the point is with the hyper-heuristic, we don't want to rely on a single algorithm, but we have those multiple operators or heuristic, and we can apply them and pick them through the search process. And the other main element we need if we devise a selection hyper-heuristic is having a move acceptance criteria. So what it simply does is you pick a heuristic, right? And you apply it. It's going to generate one or more solution depending on what you have. And then you need a mechanism which can tell you whether it was a good solution to accept so that we can continue with it, or it's a good idea to reject it. But to give you a simple perspective, for instance, if the solution is better, you probably want to keep it, right? Accept it. If not, you might prefer to reject it or accept it with certain probability or chance for the sake of providing exploration in the search space. And for the heuristic selection part, there are many different heuristic selection algorithms, but the main idea is essentially linked to reinforcement learning from machine learning. So the idea is you consider, as a simple example, you can consider those heuristics or operators as like actions, and you're trying to find the right action at a given state, right? So you can find a lot of algorithms in reinforcement learning or the variation or the simplified version of it. But to give you a better flavor of the heuristic selection, I would like to give you this example. So in here on this slide, you're seeing 6 different problems. I will come back to these problems later again. And one is bin packing on the left top, then maximum satisfiability. Satisfiability is a decision problem, maximum is the optimization version. And we have the personal scheduling problem, which is essentially nurse rostering. And the left bottom permutation flowchart scheduling, which is another common problem you could see in the literature. Traveling salesman problem, which is one of the oldest, right? And we have the vehicle routing problem. So in this graph, what you're seeing is on the vertical axis, you're seeing the number of heuristic calls, which simply means that if you look at every single plot, every line refers to one heuristic. Then you're seeing which one is called more often than the other one. Or you can see that the selection regime is changing over time. So that's why we have the horizontal axis reporting the time in terms of 10 minutes, right? So in here, one thing you see is that, and usually there are like a changes of the selection, right? Like if you look at the, for instance, max set, you're going to see that we have this purple line, right? It wasn't selected too, like it wasn't favorite at first. It was in top 3 though, but then it took the lead over time, right? Or you can see that we have the green and also another green one with open color. And you're going to see that they getting closer in terms of the calls, but then the one of them is being called more later. The reason is being that when you're working with optimization problems or computational search problems in general, you might end up seeing that there are different regions, search regions, requiring you to change the way you solve it, right? Because you could have maybe a lot of local optimas, or you could have flat spaces. It doesn't allow you to get a lot of feedback when you're searching. Okay, but so now we have seen the hyper-heuristics, and I talk about the selection hyper-heuristics. right? It is cool. It can solve different problems, problem independent. I can apply to anywhere. And if I have a good design in terms of generality, I will be super happy, right? Another question is, if this is that good, can we use it as, can we consider these as like an ultimate solver you would use for computational search problems? And these ones are the numbers you are seeing from a competition roughly 10 years ago. It's from a hyper-heuristic competition. And on the leftmost column, you're seeing algorithms competed in this competition, right? And then we are having this total score in the second column, and the remaining columns are showing the score with respect to each problem domain, right? And we are seeing the same problem domain if you realize, right? MaxSat, bin packing, flowshop scheduling, personal scheduling, TSP, and the vehicle routing problem. So by the way, this is scored based on something called F1 score. If you don't know it, that's okay. If you see a higher number, it means that it's better, right? So if you look at the overall result, the best algorithm, best performing one is the GIHH. It was actually belonging to me. There's like a high score margin compared to the second one. That's great, but the life may not be that great. Let's look at the individual performance now, right? It was also best on MaxSat, also best, quite large margin on bin packing. On flowshot scheduling, it wasn't the best, the second best. The third hyper-heuristic ML came the best. If you look at the personal scheduling, it is doing really bad job, right? If you compare to the second algorithm, the first one is pretty poor. For TSP, is also doing a great job, but VRP, average or below average, right? With 15, while the P-Hunter take the lead. So as you can see, even though we have these algorithms, they could be adaptive. We are injected a lot of machine learning in it, right? And it's general, so it is applicable. That's all good, but still we are facing the issue of no-free-lunch theorem. So on theory, we have this, but also in practice, we are seeing that even though we have those algorithms, we can see the cases they do actually a bad job while doing great job on other cases. So the whole point is we cannot just trust hyper-heuristic if we really want to come up with a great solver, right? Even though they are great, but we want to have really like a solver which can work every time or most of the time, and providing potential best or close to best performance. That's the kind of the ultimate goal what we're pursuing. So now let's see how can we do that, right? We can get help from algorithm selection. But before explaining that, let's see a table I randomly picked from a totally random paper. And this one is showing you a list of traveling salesman problem instances if you look at the leftmost column, right? GR24, Berlin 52, and the rest, right? And the remaining columns are showing algorithms, right? They are from ant colony optimization, but it doesn't matter, right? The first one is called AS, the second MMAS, third one is ACS. If you look at the first problem instance, what you're seeing that the algorithm AS has been the best one, and here lower is the better, right? And if you look at the second problem instance, Berlin 52, you're going to see that MMAS is the best. And if you look at the SD70, which is the third algorithm, MMAS is again the best. But if you go below the bottom, red 783, you're going to see that ACS is the best algorithm. So as you can see, when we have these studies, the papers comparing these algorithms, they're a bit tricky. Saying an algorithm is better is a bit tricky, right? If we have, there could be one better algorithm, but if you pick the instances in such a way that one algorithm is really good at, you can show that that algorithm is better. So long story short, as I already explained with the exemplified with the hyper-heuristics, so in regular algorithms, more of traditional ones, and we can see that some algorithms work well in some cases and doing a poor job on others, right? The goal is, can we come up with a system picking the right one at the right time, right? So the basics, so that's why we have the algorithm selection, which is aiming at automatically picking up the best algorithm out of the candidate algorithms you have for a given problem instance. By the way, there are variations of the algorithm selection, but here I'm referring to the one called per instance algorithm selection. So picking an algorithm for a particular problem instance. I'm showing this figure, which is essentially showing some SAT solvers who will satisfy the problem, where the algorithm selection got its popularity initially, right? Now see how it works, right? It is pretty simple. So what we are going to do is we will just build a prediction model. Then it will be already used for picking the right algorithms. Of course, it doesn't always mean that it will pick always the best, but at least that's the goal, right? And what we do is for this one, the goal is the prediction models we want to devise is essentially predicting performance of the algorithms, right? Like in this example, we had these 3 algorithms, right? If I'm gonna get for instance, the instance 5 TH150, I want to predict whether AS, MMAS, or ACS, which one is expected to be performing the best. Then I can pick that and use it to solve it instead of relying on one algorithm, because I know that one algorithm will not necessarily provide the best overall performance. So for this reason, we need of course data. To be able to data, we need some training. We need to do some training, and in terms of training, we need to have a set of algorithms. And that's what we call as the portfolio. So we are going to have those candidate algorithms. Like one example could be these 3 algorithms you're seeing on the slides. But of course, again, the portfolio is another topic, like picking the a good ones complementing each other, which would be, of course, a better portfolio. But let's assume that we are not doing that. We are just having an algorithm set and using it. And then we are going to need a number of problem instances, right? And after that, what we need to do is we need to get those algorithms and run all those instances we have, and which will lead us to have a performance data, which simply says that for every problem instance I know which algorithm doing what, right? And the other thing we need in here, of course, there are different versions of algorithm selection, by the way, but mainly what you need is you need to have a set of features which are characterizing the problem instance as well, right? To give you an example, maybe you want to devise a system which can solve the TSP problem. Maybe one kind of the TSP problem instance feature, the characterizing feature could be number of points or the cities you need to visit, right? And based on those bunch of features we have, we are mapping this to the performance data, and we're basically using, again, some machine learning algorithm which will do the prediction. And whenever we have any problem instance, what we need to do is first extract the features representing it, and give it to the model, and model will tell us what are the performances we are expecting of the algorithms we have on this new unseen problem instance. And based on our prediction, again, the basic idea, there are variations, but the basic idea is picking the one which is providing the best expected performance, referring to our model. And now let me show you one example. And this is an algorithm I developed some years ago. It is essentially an algorithm which is also called as recommender system. So that's why it's called algorithm recommender system. One trait of it is using collaborative filtering. If you know that if you use the recommender system, in one type, what they do is you have like user specifications and you have preferences on what kind of items you like. Maybe you're in a like e-commerce website, and a system can make suggestions based on your preferences and your personal details like your age, gender, and whatever, right? But in the collaborative filtering, the idea is a bit different. Instead of looking at those kind of features, you look at the preferences. And the basic example given the collaborative filtering is like a movie data set, right? Think about, we have a lot of movies like IMDb, right? And we have the users, and every user gives some score, right? It could be like 1 to 5, for instance, or 1 to 10. Then what we do is by looking at the similarity between the users based on their earlier scores, and we try to make a prediction on the scores we don't know, right? So if I watch some movies and the other guy also did that, the same ones, and we know that we have similar taste, and if the other guy watched some movies which I didn't, if he liked them, I expect that I will also like them, right? That's the idea. So we kind of take this idea and say that the items for the users for us are the items or instances. So users for us are the instances, and the items like movies are the algorithms. So the question is whether an instance will like an algorithm or not. Okay, and for the mapping in here, what we are using simply random forest, which is a well-known ensemble learning algorithm for machine learning. You could use something else as well, and there are many other machine algorithm selection methods readily available. This is just one of them. But this others doing in one side is through collaborative filtering, but actually we are not going to benefit that too much. That one is super useful when you have data which is incomplete. Like if you refer to that study, you could see that maybe you have, because the generating performance data in the first place could be expensive. So maybe you have data which is partially collected with the performance data, right? You don't have a full picture, but you can still devise good models with this algorithm. But actually the prediction task, the selection happens in this, they explained in this slide. And what we do is instead of mapping features to the performance data, we are mapping features to features. And when I say mapping features to features, what I'm doing in here is we have the performance data, right? Remember, which is made of algorithms and instances. And we are simply applying matrix factorization, as you understand, is factorizing the metrics we have, the performance metrics, which is resulting in multiple submatrices, which are factorized versions, right? And so if you multiply them, it's going to give us the original one or approximate it. So in here, we are using SVD, singular value decomposition. If you don't know, maybe you have seen this in linear algebra class, but if you don't know, it's something like PCA, right? And what we have is in here, when we apply this, it's going to generate some matrices. And one of the matrices, like in here, you're seeing MN matrix, think that M is the instances, N is the algorithms, right? And then R matrix will be the metric representing your instances. And the N, the matrix on the rightmost side, it will the matrix representing your algorithms. Okay, so then we actually extracted features directly from the performance data. They are actually more reliable if your performance data is extensively generated. You can rely it more because you extract features just by looking at the performance of the algorithms. On the other hand, you're picking some features and maybe the features are not reliable. There are conflicting stuff. Maybe they are not good enough for the machine learning algorithm you're using, right? So that's why what we basically do is, in that sense, we are moving from the original feature space to the latent, the hidden feature space. We extract it through a singular value decomposition, but you don't need to use that only. You could use any matrix factorization technique to do that. And this is the algorithm, which is basically explaining what I told you. But one thing to mention here, because we are devised this idea as a recommender system, and if you recall in the recommender system, especially in the collaborative filtering, the form of the data is usually including ranks, right? So like the rank of movies, rank of songs, right? We have some discrete or integer scores. So to be able to kind of get the same idea, what we do is we take the performance data, which could have total strange numbers, we just convert them into rank metrics, right? So then our performance data now looks like the rank of the algorithms, right? The first algorithm gets the rank 1. The fifth best algorithm gets the rank 5, right? And when we get the model, our prediction is this: we get the features we extract for the Neve problem instance we got, and we are predicting the feature for the middle matrix, right? The one you're seeing, the second one in the shape, right? We are going to predict a new row for that matrix. And we are going to multiply with this other two matrices. It's going to give the row of the original matrix as the prediction, right? That's basically what is happening with the pseudocode. Okay, let's see how this works, right? So now the idea is, I already mentioned that we have those hyper-heuristics, right? And even though they are good, they have some level of generality and they are doing a great job on different problems, but still they are not enough, right? There's still a gap to go to be able to have even better algorithms. So now we are just replicating the idea of algorithm selection, but here the algorithms are hyper-heuristics, right? That's the main idea in here. So it means that now we don't have one hyperstic, but we have a bunch of candidate hypersticks. And what we're going to do is we are going to automatically pick the right one, referring to problem instance currently we are trying to solve, right? But of course, we have a challenge. So the life is not that easy always, right? So we need to come up with a set of features. Like if you go back to the algorithm selection, what people do is they come up with these features which are problem specific, right? I told you as an example of a TSP, right? Like one feature could be the number of cities or the data points you're expected to visit. But a problem with the hyperheuristics, we cannot just take this idea immediately because the hyperheuristic are supposed to be problem independent, right? If I inject some problem related data or information to the hyperheuristic, it will be defeating the purpose of the hyperheuristic in the first place. So to be able to keep things still problem independent, respecting the domain barriers. So again, when I'm applying this idea, I don't know which problem I'm solving. I don't know what is the instance, right? And so for this purpose, we developed 39 super simple features and referencing some of the work I have done before. And these are the kind of the titles of the features. We have some basic ones. And the second group is based on the fitness values, like the quality of the solutions. And the third one is time-based. And the last one is the mix. So we are combining different features from different groups. Okay. Of course, this looks like a bit messed up, but these are kind of showing some of the features. For instance, from a basic feature, one feature could be the number of heuristics. The other feature I can tell right away from here is like a number of best solutions found by a particular heuristic, right? But before that, let me tell you how we generate it. So to generate it, we apply something super simple. So we have this hyperheuristic, simple random improving equal. So it's simply randomly pick heuristics. And as the accepting criteria says improving equal, it simply means that if the new solution is good as the earlier one, we accept it. Better, we accept it. Worse, we reject it, right? That's it. So what we simply do is we pick the simplest hyperheuristic and we run it for 10 seconds on the instance to do a feature extraction. Right, and also we have one element for accepting worsening solutions. And here it is just 10%. Again, this is not tweaked or anything, just designed this way and run it and used it right away. So this one, we are generating those numbers, right? As I said, like a number of new best solutions found by a particular heuristic. And for time-based feature, for instance, how much time your heuristic is taking on average when it's applied to that during that 10-second period, right? Or we have quality-based features. For instance, what is the difference from the worst solution you visited and the best solution you visited in comparison to the average solution quality you got? And the mixed one, as I said, they're just combining these different times, right? So now the good thing is we have the features which are problem independent. So these features could be derived for any computational search problem, basically, where you can quantify the solution quality. Okay, let's see some results, right? But before that, I would like to talk about the experimental setting. I earlier mentioned the hyper-heuristic competition, if you recall, and it was actually utilizing this framework called HyFlex. And HyFlex is essentially a hyper-heuristic framework where you can implement different algorithms, hyper-heuristics, and different problem domains. By nature of implementation of the design of the framework, they are independent, so they don't directly interact, right? So there is a domain barrier. So that's kind of the trick they have. And in their version, and initially they have this four problems: Boolean satisfiability, which I mentioned earlier, bin packing, permutation, flow chart scheduling, and personal scheduling. And with the competition, they released two more: traveling salesperson and the vehicle routing, right? So in total, originally they had those 6 problems. And the idea is you come up with an algorithm which can solve these 6 problems as good as possible. Okay. And then for every single problem, we have different types of heuristic sets, right? if you look at so here you're seeing a graph, which is a chart, which is saying like every element you are seeing at the horizontal axis is referring to the problems, right? MaxSat, bin packing, flow-shop scheduling, personal scheduling, TSP, and the VRP. On the vertical axis, you're seeing the number of heuristics. So as you can see, for every problem we have different number of heuristics. So this is a good scenario for generality, right? But beyond that, we have one more difference. Here they defined heuristics with respect to certain types. And one type of the heuristics called mutational. So it simply means that you have a problem solution you generated. You simply make some small or big changes depending on the heuristic, on the solution, manipulate it, and generate a new solution. To give you a simple example, if you're working on a TSP problem, a potential solution will be a permutation of the cities. And maybe like swapping two cities in your solution could be considered an example like operator we could do. Or simply mutating it, like you can simply changing the value with something else or some other value or part of the values. And the second group is ruin and recreate. So it means that you're gonna pick a part of the solution you have and remove it and regenerate that part. And we have the local search. I assume you know it already. So we are trying to find a local optimum point by using those algorithms, right? They will keep searching the neighborhood and return the best one they can find. And then finally, we have the crossover, which is something you know from evolutionary algorithms as well as the mutational ones, right? And with the crossover, the idea is we have more than one solution. It could be two or more, and we combine them and generate new solutions out of them. So we have these 4 types for every problem, and the number of, again, the heuristics set sizes are different, and their distributions are also different, right? If you look at the first heuristic set for the max set, they're widely covered with the mutational heuristics. But for the bin packing, mutational is comparatively less than the max set, right? But of course, this wasn't good enough because this was kind of an old work already. And there has been developments on the HyFlex or adding more problems because of the hyper-heuristic community. And so we have this another study, which is not that new also, but newer compared to the original HyFlex. And they extended HyFlex setup with 3 more problems, right? 0-1 knapsack, quadratic assignment, max cut. So now the task is to solving this 9 problems at once. But before moving on, I would like to further discuss this table a bit. And you have the second column in here, you're seeing the instances, which are showing how many problem instances we have for every problem. So like for MaxSat, we have 12, bin packing 12, FSP 12, MaxCut 10, right? And on the third column, what you're seeing is the number of low-level heuristic we have. For the first problem, we have 11. For instance, for 0-1 knapsack, we have 16. For bin packing, we have 8. And for the parentheses, we are seeing the types, right? Like the first one, the MaxSat, 6 mutational, 2 crossover, 1 ruin and recreate, and the 2 local search. So the heuristic sizes are, set sizes are different, and the distribution of the heuristics are again different. So overall, going back to the algorithm selection idea, we need to have a data set, right? And as I said, we need to have a bunch of algorithms and the problem instances so that we can do some training in terms of machine learning. So if you sum everything up in terms of the instances, you're going to see we have almost 100 instances. Okay, it should be not 6, 9 problem domains, right? Almost 100 instances, 98 instances from 9 different problem domains. So that's why it means that we need to generate a performance data out of some hyper-heuristics, and which are the 6 of them, right? And here you're saying the 6, and some of them are from the competition I mentioned you, right? GIHH, it was mine, EPH, another one. And also we have this iterative local search variation and 2 kind of poor or simpler hyper-heuristics. And again, this is also from I believe from the same paper as I mentioned in the extended version of the HyFlex. So now what we have is we have the performance data set of 98 by 6. So 6 algorithm, 98 instances. That being said, this data set is kind of small actually for algorithm selection, but let's see what happens. So this is actually the result right away, before further discussing the details. On the leftmost column, you're seeing the problems, right? Max set, bin packing, and whatever. And on the remaining, the other columns on the right-hand side, we are seeing 6 hyper-heuristics. And the first red, you're seeing ASHH. It is essentially the cross-domain algorithm selection method, and here using algorithm selection on top of hyper-heuristics. And on the rightmost side, we see the oracle, which is also called as virtual best solver. It simply means that what will be your performance if you always pick the best hyper-heuristic for every single problem instance. So it means that this is the best we can do if our selection method is best, right? And at the bottom, we have 2 lines, P average or O average. And a P average is saying, taking average with respect to the average ranks across the problems. And O average, we just make a big table of 98 problem instances and just average them. And when I say average, we are averaging the ranks, right? So if you have a lower value, it means that your algorithm is ranked better. So if you look at the average performances, if you purely look at the hyper-heuristic, the best one is the one on the third column, right? NRFS-ILS, it has been the best performing one. But if you look at the algorithm selection, it has been much better than that, right? With around rank 3, while the NRFS-ILS for rank 4. The other one are close. Of course, the other AH and ANWHH are the bad ones because they were super simple designs. But before moving on, one thing to note, even though I got the best performance overall, it is not necessarily the best for per problem, right? If you look at the max set, FSILS is the best one. Algorithm selection is doing 2.5 rank, while the FSILS is doing a little bit better, right? Or if you look at the beam packing, algorithm selection is 375, EPH is the best one. For that problem, 346. So individually, it's not the best, but on average, it's the best. And because that's we are like also in the competition or in the hyper-heuristic, we are looking for the overall performance, not the individual. So that's why it shows that we kind of eliminate some of the issues we face with the hyper-heuristics. By picking different hyper-heuristics, we didn't design any hyper-heuristics. We didn't design any algorithm. We used super simple features, which could be derived easily. And we already beat the hyper-heuristics pretty well with respect to the average performance. But one thing to note here, why it, even though it is best on average, it is not always best for the individual problems, is we have really limited data. So I'm going to talk about a bit on the feature research, what we are doing to kind of eliminate that. But still also, if you look at the oracle, which is reaching to rank 197, so it means that our algorithm selection is not perfect yet, right? We still have some gap to fill anyway. And this one is showing you the selection of the hyper-heuristic with respect to oracle. Again, the optimal selection and the cross-domain algorithm selection, which is on the right-hand side. Of course, the selection is different for different problem instances, but if you look at the overall picture, there's some level of similarity, not necessarily the same. For instance, the oracle is picking this ADAPT-HH, which is actually GIHH, more frequently, while the selection algorithm selection is picking NRFS-ILS, which happens to be the best overall single hyper-heuristic, right? And yeah, this poor hyper-heuristic actually could be useful in some cases in the oracle. It is picked because there are some cases all the algorithms returning the same performance, so you cannot really differentiate. So that's why picking any of them will be the same. So that's why sometimes those better hyper-heuristic could also be picked. But for selection case, algorithm selection, it doesn't pick that at all. If you look at the individual problems, you're seeing how much of the selection is optimal. So like you're saying, the max set is pretty optimal, like pretty close to the optimal selection, but for TSP, it is just 10%. Like for max set, you can say, wow, that's amazing. For TSP, it is really poor. It is not necessarily that way because this is assessing the optimal selection. Because if you look at the algorithms, we had 6 of them. Like for instance, the second algorithm performance could be already pretty close to the best one. So it means that even though maybe we picked the second best, third best, the result could still be good enough or close to optimal at the end, right? So that's why, of course, if we have probably more data, we could have get closer to the optimal selection regime. And the other thing we have is a simple analysis. If you recall, in the algorithm selection method, we were using random forest. And random forest is an ensemble algorithm. What it simply do is just using subset of the features and building a lot of decision trees. And based on that, it is able to identify which feature is contributing more to the model is generating. And here in this graph, you're seeing the features. You don't need to read the features because they look super complex, but I'm going to tell you the one you're seeing, the purple or bluish ones, right? These are the best one with respect to Gini index, which is again the measure used with in the random forest, or is a generic measure used in the ensemble algorithms actually. And these are the top features, which are substantially more critical than the rest. Even though the values are still close in terms of the Gini value. And the most important feature we picked was the ratio of the number of improving solution explored compared to the equal quality solution, right? So based on this number, this ratio is essentially telling us the whether our algorithm will work well or not on that particular problem scenario. This is actually interesting because if you think about the equal quality, it essentially tells you the neutrality of the search space, right? Whether you have a flat space or not. Then your neighboring solution or the solution you visited will be giving you the same quality. But then we have the improving solution. It means that how often you can make improvement, which means that you have a more chance to improve the solution in the solution space. So the ratio is essentially tell you that whether you can improve more or you need to deal with this neutrality issue, right? So it makes sense. The second feature is telling you the difference between the best solution you found so far and the worst solution through a whole, through the run of that 10-second I mentioned for feature generation. And we also divide it to the average. So this is simply telling you the range of solution you're actually visiting with your algorithm, right? How far it can go from the worst solution you have, or how worse it can do mess up the most. And this feature would basically tell that. And the last one, the third best one is the worst solution quality compared to the initial, right? And this comparison is also telling us how bad we went compared to the initial solution, or didn't go bad, right? And we are always doing better. That's also possible. So long story short, these are giving you like a kind of an understanding. If you look at those features, you're likely to do your selection better. But we didn't pick them by hand, but it is just what we get automatically from the results of the algorithm selection. And because I told you that in the SVD, when we apply the matrix factorization, we are having those features representing the instances and the algorithms, right? And here I'm just showing you how they look like, the instance space. Right here, you're seeing the hierarchical clustering of the instances. Maybe the numbers are a bit small, the text. So like every text you're seeing referring to one problem instance. So based on that, you can actually identify which instances are kind of similar, which are different. But to give you an example, because we are talking about the cross-domain algorithm selection, like a bin packing 0, meaning that the first instance in the bin packing benchmarks or the instances, and the TSP8 instance, they're rather comparable, even though they are coming from totally different problems. Also, NRP2 is kind of comparable to NRPs, the nurse rostering or personal scheduling, is rather comparable to the flowshop scheduling instance with index 9. So that was basically all. Just to wrap up what we have seen, the algorithm selection can outperform the individual selection heuristics with limited focus, right? We didn't develop anything new. We didn't inject some fancy machine learning algorithm. We didn't even have enough data, right? But we still are able to get something better than the algorithms which have been developed really maybe a long time with a lot of thinking. So now what we are doing is, of course, this small data set wasn't the ideal case. Now we are extending it we already have an extensive set of this problem setup, right? We have a lot of problem instances right now, and we are testing a lot of hyper-heuristics. So we are collecting a really big performance data, and of course also adding the additional ones compared to the one here, which just says 6. Now we have more than 20, I guess. And the next thing we are also looking at having this portfolio. I quickly went over that, but the portfolio essentially means that instead of like throwing a lot of algorithms, you just pick a subset they are complementing, right? So you have like an algorithm one, which is probably doing a certain type of problems, and algorithm two in other problems, right? This kind. Of course, we don't want to do it by hand, but there are automated approaches to do that. Yeah, that was all basically what I want to tell. And if you have any question, I will be happy to answer.